Good.
You?
Making it. So how's everybody's weekend?
It was awesome.
Do anything fun?
My Sunday morning was really good.
Yeah. Have fun at the OCC?
Yeah, it was a lot of fun. Yeah, Mike was really good.
Yeah. He's a good guy. All right. Well. Let's see here. So today we're going to go over some air masses, fronts, and then the theory of a storm system. So what I want everybody to do. So I want to start out with this video. If I can grab it. Let's start out. Watch this video, and these video links are in the Google Drive as well under today. But we're going to start out with this video. It's about 8 minutes long. Just talking about air masses, and then we'll go over and review some of this stuff.
Quick question, did anybody else have difficulty opening one of those other links?
I did. It wouldn't open for me.
Yeah.
Is this one giving you problems?
No, one from Friday that you asked us you asked us to watch a video.
Yeah.
At the end, and it did not open.
The turbulence one wouldn't open for me.
Really?
That's the one.
It would take me to YouTube and then nothing would load.
Okay. Well, I will find the video and get it reposted for you guys to watch tonight. So yeah, everybody go ahead and watch this video. Let's just plan on getting back on as soon as the video is over. I wasn't recording anyway, so you guys don't have proof. So the highs, think of it as like a raised spot on the map, okay? So the highs are rotating clockwise and down. And the lows, let's see. Think of them once again as a dent, but they are rotating counterclockwise and up. Okay. So what we have here is when a low converges with a high, we've got what happens is we develop what we call a front. Okay, and what a front is is where a warm air mass is trying to overtake a cold air mass, or vice versa. The lows tend to want to overtake the high, but sometimes the highs can push the lows, kind of like a snow plow would. These frontal systems is where we see weather develop. Okay. So what happens is we get this lifting force that happens, right? In those areas. Let's see. But what's important to remember about these lows and highs as well is that, let's say that let's say that we have a low over here. Once again, what's happening is these winds, remember the low's rotating counterclockwise, right? So what's happening is these winds are going to be coming over the ocean, picking up moisture, and bringing them into the land here. So let's say we have the low pressure system here. These winds, it's going to be grabbing these air molecules and going to be pushing them in. So the wind is most likely going to be coming from the east, right? East to west, or I'm sorry, west to east. Whereas the winds up north here are going to be coming from the direct south, right? So let's say we're up here in Washington. Winds are going to be coming from the south. And the winds over here in Seattle are going to be coming from the east to the west. So what that's doing is it's cycling this moisture, right? So let's say it's a tropical, maritime tropical cell or pressure system. What it's doing is it's going to be, we're going to get a lot of moisture built up right here, which we're seeing. But up here, we're going to have a lot of dry air because it's coming over. Remember, storm systems. How do we suffocate a storm system out? We over land, if it doesn't have enough moisture evaporating, then the storm system can't develop any further and it just dies out, right? So as it's picking up this air from the ocean and meeting probably a high pressure system somewhere in here, it's developing this band of storms, right? But as the air runs out of that moisture and is pushed along this area, you can see that it basically is dry, and the winds are likely coming from, at least on the surface, are going to be coming from the east. So let's see. We have charts that depict this for us. So you can see here, well, it's really hard to see which. There we go. This is the chart I want. So you can see here, here's our low pressure, right? It's picking up, it's converging with this high pressure over the ocean here. But this pressure system is bringing in that polar maritime air, okay? So it's going to be moist, but it's not going to be saturated to the point that it starts precipitating, basically. So what you have here is you have this storm system, or this pressure system is going to be rotating clockwise and down, right? So it's bringing in this cold air from Canada. It's mixing in with this warm air here. This storm, or this pressure system is rotating counterclockwise and up. So we're seeing clouds develop along, a band of clouds develop along here, but it's not saturated to the point where it's precipitating. Man, I keep mixing this up. Oh, I was just drawing my arrows the wrong way there. Sorry, counterclockwise. This one's coming clockwise, this one's coming counterclockwise. So what we're seeing is a mixture of that air. And as it comes and meets with these high pressure systems here, so you can see that it's this pressure system, as it brings in this cold, moist air, it circulates around this low pressure system here. And as it pushes inward, we're developing this band of storm systems right here, okay? As it connects with these two high pressure systems here, or yeah, 3 high pressure systems. So right here we have a big high pressure system. Right here we have a big high pressure system. Here we have a little high pressure system that's just accelerating the winds and pushing them over the western states here. Okay, that's why we're seeing a lot of weather develop in this area. But then right here is kind of what we're seeing here. Is once again, this is rotating counterclockwise, right? And it's kind of sandwiched between these two high pressures. So what's happening is this is rotating clockwise and it's picking up all this lake effect right here and just cycling it. And because this is where the storms are converging, you can see that, or this is where the two pressures are converging, you can see that we're developing weather in this area. And it really sucked to dispatch that area today. It has all weekend, really. But yeah, so that's what's important to remember about these high pressures and low pressures is the way they circulate, right? So low pressures, we're going counterclockwise and up. High pressures, we're going clockwise and down. Okay. These troughs here, remember that the trough is just a band of low pressure, right? Elongated area of low pressure. So these troughs here, you can see that the storms will just kind of fall into these troughs and just kind of spread out to the point where they just kind of dissipate. These areas here, you see this kind of an easy way to remember the difference between your fronts, your frontal systems, is anybody guess what that is right there?
Would be a high pressure front.
Nope. So this would be what we call a cold front, okay? So think of a cold front. When you see this line here, think of these little spikes or peaks as icicles. So that's how we identify the cold fronts. And then they're also colored blue, right? And these are suns, right? So sun's coming up over the horizon. These are warm fronts. When we have a mixture of the two fronts, that's called a stationary front. So
It's called a what?
a stationary front. So
Oh, okay.
yeah, so we have two frontal systems. We have a cold front and a warm front meeting together, and neither one has enough pressure or ability to take over the other. And so they just kind of sit there. And that's why they're called a stationary front. So these stationary fronts, what happens is we see weather develop along the stationary front, and it'll just stay there. We'll see these systems, these storm systems, develop along this stationary front, and then they just stay there. And sometimes they'll stay there for days, days or weeks. This one has kind of stayed there for 2 days now. So yeah, so that's a stationary front. You know, you can see the.
I have a question real quick.
Yeah.
Actually, you're probably going to answer right here. I'll wait for this to finish first before I ask.
No, go ahead.
I was going to say, is it because it's stationary because there's not a whole bunch of one? And so is that why it's just sitting there because they're just kind of rotating by each other? Or?
Yeah, so that's what, yeah. So when you see them together like this, that means that the warm front is gaining momentum, I guess you could say. But the warm front is, if they're in a line like right here up in this corner, you can see that this is a cold front, right? So when there's more than one together, you can see that area, the one's starting to take over the other, right? So this pink one up in the corner that's hard to see, you can see an icicle and a sun right next to each other, and it's pink in color. That is what we call an occluded front. Okay, that is where we have a warm front that has moved, like accelerated, and is now overtaking the cold front. Okay, so let's say we have a cold front right here, right? And then we have a warm front right here. Oops, sorry, wrong side of the line. There we go. Okay. As this warm front converges and overtakes this cold front, we get what we call an occluded front. Okay. So we'll talk a little bit more in just a second about what the occluded front does, but but yeah. So that's a pretty basic rundown of a surface chart here. Another thing that we'll see is, remember how it talked about the continental tropical system, pressure system right here that we see a lot. what will happen is we'll have this polar tropic, or I'm sorry, this maritime tropical. And this maritime tropical. And then this continental tropical. Okay. What will happen is this will move into here, this will move into here, and then the continental tropical, continental tropical. Remember that it's bringing that warm, dry air from Mexico here. What we'll see happen is we'll see a line develop here, and it will have just a whole bunch of, it kind of looks like a warm front, but rather than having the sun spaced out like this, it will just look like a ribbon that moves along like that. What that is a dry line. This is where the the continental tropical has actually moved up, and the moisture, that moist air from this maritime tropical has converged with this continental tropical, and it forms what we call a dry line. Okay, this dry line is where you have moist, warm air on this side, and then you have dry, warm air on this side. So it's like a definite line where you'll be at like 100% humidity on one side of the line, and the other side you'll be at like 20% humidity. But that line, what happens is as a warm and a cold front converge here, cold front coming down here, a warm front coming up from here, what happens is the cold air and the moist tropical air, when they converge here, you'll get a band of weather on this side, on the eastern side of that dry line. Because you have all of a sudden have a cold front trying to overtake a warm front here. And basically it dries out the air on this side of the line. So dry lines, we see them over Texas all the time in the summer. But yeah, that's pretty much your surface chart there.
Can I just express the confusion? And it's all self-imposed, because every time I've seen a weather forecast and you see a low dropping in from, say, off the coast that's going to overtake southern Utah, we know that's associated with a storm of some sort heading our way, most likely. And I've always, in my mind, before now, considered those to be cold, moist air that that have a tendency to sink. Now I've got to read the lows are actually rising warm air.
So we're going to
screwed up. I really am. I apologize.
No, you're fine. You're fine. So this kind of leads us into, that question leads us into this this next section. So we're going to talk about storm systems here. So let me post this video in here. These thunderstorms and fronts. All right. So everybody watch this video, and we'll discuss it after you're done watching the video. But this one is about 20 minutes long. So Yeah. But that question is a good lead into this, and so we'll discuss it after the video. But everybody turn that on real quick. All right, any questions about that? Does that answer your questions, Rex?
It created more questions than it answered for me.
So hit me with some of the questions. Let's talk about it.
I'm just trying to absorb the idea of the cold air, warm air combinations, and showed a graphic of two cold air masses that were converging underneath a warm air mass.
Mm-hmm.
Uplift, and I can understand the uplift because it would drive the warmer air up, which, if there's any moisture in it, will create clouds. It's just, I'll have to go over that one and just take each section little by little. But I don't want to hold them back. So.
Oh no, that's exactly what we're talking about anyway. So, so as we were talking about on the surface chart, we identified the different front systems, but what we see, this is a cross section. So this is, a lot better visual of what's going on. So if we have a cold front, what we have is a cold body of air that's moving underneath this warm body. So this warm air is taking over the cold air. Okay. So as the warm air moves up and over the cold air, what we have is convection, right? Whenever we have that rapid rising warm air, we're going to have convection. And what that causes is the thunderstorm to develop. Okay? It's basically the same thing as a warm front. When a warm front, so we have a warm front, we have the cold air, the warm front's overtaking the cold front, or the cold air. This is just much less violent. So when we have the cold air pushing underneath the warm front, it's a lot more violent of a storm system that will develop. Okay, so
Yeah, one more time, just that last part, when you have, what is it that develops the more severe thunderstorm?
So a cold front, when we have the cold front moving underneath the warm front, as you can see here, this creates much more violent of a storm system because it's pushing that warm air up at a faster rate. So we get a lot quicker of a storm development. A lot of times what we call these are going to be, we're going to, like over the Salt Lake Valley and St. George and places like that, it's going to develop an air mass thunderstorm. But basically, the storm system will see these clouds develop in 15 minutes. You remember the video talking about them. Just they pop up really quick and then they dissipate. Okay, so you'll see cumulus clouds go from just a little fluffy cumulus cloud to a full-blown anvil top in a matter of 15 minutes when it hits that mature stage. and once it hits that mature stage, it starts dissipating, and that's when we get the precipitation. So as it's building from a cumulus stage to a mature stage, it's not really raining at that point. When we see the precipitation and the heavy rain and the hail come is when the storm actually starts dissipating. But yeah, this is much more violent of a thunderstorm. This is when we see them just kind of explode, right? Whereas when we have a warm front pushing over the top of the cold front like this, identified by the warm front on our charts, it's much more smooth of a storm system buildup. It's much more stable. So that's the correct term for it, is stability and instability, right?
It makes a lot more sense.
Yeah, the cold air is the cold fronts are much more unstable than the warm fronts. So when we have an occluded front, basically neither one, it's just a struggle for power. Or I'm sorry, stationary front, it's just a struggle for power. So we'll still have the warm front, the cold front stationary, the warm front's trying to move up over the cold front. So it's a lot more stable of a storm system and a lot more longer lasting of a storm system. So this occluded front is what you were talking about, where you have a cold air mass catching up to a cold air mass here, right? And we have a warm air mass over the top. So as this cold air mass overtakes the warm air mass, it creates, and this cold air mass is trying to connect. It creates this really violent area of thunderstorms. The cold air fronts will basically push the warm air up at a quick rate. So what we have happen, typically when we have these occluded fronts happen, so yeah, like it says here, as the two fronts merge, the occluded front forms, and at the occluded front, the cold air undercuts the retreating cooler air mass associated with the warm front, further lifting an already rising warm air. So you've got warm air already rising as it's over this cold front, and then it converges with this warm front, and the cool's trying to overtake the other cool air mass. It's hard to explain it, but yeah, because you already have the rapid rising air from the cold front and the more stable from the warm front, the occluded front causes an even more explosive weather pattern to develop. So the next thing that she talked about was the wave cyclone model, right? So you have two air masses that are passing by each other, and remember they rotate in opposite directions. So so what we have happen is when the low pressure wave forms, so you have these two fronts converging, creating a stationary front. As the low pressure wave forms, so you'll see it start building right here. We start to see rotation occur. As that rotation continues to build, that's when we see and you can see it on our aviation charts here. Let's see. Oops. Oh, I already have it up. You can see this exact thing starting to happen here. You have this stationary front. Most likely we're going to see an occluded front occur or start to form over Michigan here. But as it starts to build there, we start getting rotation. And when we look at the radar, you can see these areas where these frontal systems are converging, and we start getting, so this is hail, but you start getting rotation. So this right here, TVS, that's talking about there's rotation building in this storm cell. Okay. You can also see that over here, but it's kind of weird. The surface chart is a little different looking than what we have going on here. Remember that the surface chart is a forecast, but these areas where you can see this TVS, that's where we're starting to see rotation, a tornadic rotation. Let me see. I wonder if this will. There we go. Yeah, you can everybody, let's see if I can walk it through. You can see these, when these two fronts converge and start turning into that stationary front, you can see the occluded front form off the edge here. So let's move forward just a little bit further. Oh. So if you remember the radar that we were just looking at, let's see if I can go back. You could see the stationary front there. Well, as it's showing you guys right here in this, you can see that as those two fronts converge, as we get a stationary front, you'll start seeing that build and curl around, kind of like we saw on the on that surface chart I was just showing you. As that builds and curls and that rotation continues to build, that's when we start seeing those tornadic warnings there. Remember that there's a difference between a funnel cloud and a tornado, right? So a tornado is when it actually touches the ground. funnel cloud is when it's still above the ground. And as it talked about in the video, these funnel clouds can actually be quite deep. So you may not be able to see a funnel cloud. You may not be able to see the tornado forming, dropping out at the bottom of the cloud, but it may be rotating up in the cloud still. And that's the funnel cloud. So again, part of the reason why these learning these fronts and how they act with one another is so important, is because we need to be able to look at these charts and understand where we're going to be seeing weather happen, about how far out we can guess it's going to be happening, but we need to be able to look at these charts and just go, oh yeah, we've got a stationary front here, we've got another one right here. Our low pressure here is pushing into this high pressure. We've got a warm front. This is going to be a much more stable storm system. It's going to be a little bit longer lasting of a storm system, whereas these this low pressure here will probably develop into thunderstorms along the west coast here over a certain amount of time. Probably in the next 8 hours, I would guess. Probably see some storm systems develop over the coast here, but we need to be able to look at this and get an understanding of our air masses in the movement and what to expect as far as weather goes. So does anybody have any questions so far? So why don't we take you guys want to take a 15 or a full-blown dinner break?
I'm good with either.
I
good
would
with either
prefer a
also.
dinner break.
Yeah, dinner works.
Okay, so let's do 30 minutes tonight. We'll jump back on at 7:20. How's that?
Sounds
Deal.
good.
All right, everybody back?
Yeah.
Yeah, I'm back.
All right. So let's talk about dry lines real quick. All right. So can everybody see what the dry line looks like there on the charts? So you've got this line, and then you just got the little bubbles along the line all the way down. This computer is just not my favorite. Okay. So dry line is low level boundary, hundreds of miles long, separating moist and dry air masses. Like I said earlier, it typically appears over Texas, in the south there. But as you can see here, it comes from the continental tropical and the maritime tropical air mass systems. Okay, so typically advances eastward during the afternoon and retreats westward at night. However, a strong wave cyclone can sweep a dry line eastward into the Mississippi Valley or even further east, regardless of the time of day. So if we got really strong winds occurring, it can push the dry line further east. Okay. So low-level clouds and early morning fog often prevail in the moist air, while generally clear skies mark the dry side. Severe and sometimes tornadic thunderstorms often develop along a dry line in the moist air just to the east of it, especially when it begins moving eastward. Okay. Typical dry line passage results in a sharp drop in humidity, clearing the skies, and wind shift from the south or southeasterly to a west or west southwesterly. Blowing dust and rising temperatures also may follow, especially if the dry line passes during the daytime. These changes occur in reverse order when the dry line retreats westward. So, let me show you. What a dry line looks like from the air. That's one picture. And a really I don't know how to spell. Kind of like an eyeliner, you got the dry liner. pretty crazy to actually see, because you can see a definite line between the dry side and the moist side, right? So you can see, it's got it on this graph, but you can see the definite difference between the dry side of the dry line and the moist side, right? This one you can see that we've got rotation occurring as well. I guarantee that there were tornadoes that developed in this storm system, but yeah, it's kind of crazy how definite of a line. I mean, this one doesn't have the dry line marked, but you can see where the dry line is occurring. But another interesting thing is the wind. You can see these wind flags here. Okay, you got your treble clef there. Okay, so you can see the difference in the wind. This one you can see is the winds are a strong westward wind. Okay, and this one you can see that strong south easterly wind. Okay. But yeah, really interesting to actually see what it looks like from space. Any questions on any of this? You guys are so quiet. Let's see. Here's something kind of interesting to note as well. This right here is your humidity. So you can see 70s, 60s, but on this side of the dry line, 19, 12, 20, you know, as we get closer, 36, 37, but a pretty stark contrast from the 63 right on the other side. And this is what it looks like on a radar summary. So these areas of the dark red, that's areas of very strong, heavy precipitation. Orange is moderate, yellow, light, green, drizzle. Okay. But kind of interesting to see how it just butts right up against that frontal line there. Okay. So we talked about thunderstorms in that video. And we've really beat the thunderstorm thing. So as we talked about before, the 3 stages, and this is important, I'd write this down because this will be on your tests. The 3 stages of a thunderstorm are going to be your cumulus stage, mature stage, and dissipating. Okay. So in the towering cumulus or the cumulus stage, as we already discussed, we see the formation, right? It starts as a small cumulus cloud, but we see that rapidly build to a mature stage. Remember that between the cumulus stage and the mature stage, the average time it takes to form into this towering anvil top is 15 minutes. Okay. Once we hit this mature stage, so in this cumulus stage, as I said before, this is all going to be updrafts. What we associate with the cumulus stage is just extremely strong updrafts. Okay, there's not precipitation yet because of the strength of the updraft. What we have is basically this air is just circulating and building, but it's not allowing the rain or the precipitation to escape yet. Okay. As we hit the mature stage, the downdraft side, you can see, so we're still building, right? The storm's moving in this direction. Storm's still building, but the storm's not moving in that direction. It's moving in this direction. Okay. As it comes over the top of the frontal system here, over the cold front of the system, what we see is it stops building and starts strong downdrafts. Okay, so these extremely strong downdrafts are going to allow things like rain and hail to start escaping the cloud. Okay, so as it said in the video, the strong updrafts followed by a strong downdraft. Basically, you don't want to be anywhere near the storm cell when it's at this point. If you try to go under it, you're going to experience the strong downdrafts and extreme turbulence. Whereas with the updrafts, you could get it basically turns this cloud into a washing machine, right? On spin cycle. What we see happen in this dissipating stage is we see the clouds stop the convection going up, and we just see the cloud start dissipating, right? So what's happening is it's just dumping out all the water that just occurred. Okay, the hail that has been building during this stage, as you remember, those super cool liquid drops, they freeze as they reach the peak here, this colder upper air. And then as they come down, they get picked back up by an updraft, and more of those super cool drops continue to attach themselves to this for this start of the hail. As the storm starts dissipating, we start seeing the hail. You can see that these anvil tops can go really far out there, but we'll see the hail and the rain sometimes. Most of the time, you're going to see the rain and the hail really start dropping very far outside the storm. Not necessarily where the cloud built itself, but you can see the hail actually dropping miles and miles outside the storm. But sometimes you'll have, it'll end right here and you'll still have hail clear out, 5-10 miles away happening because of the strength of the storm. And it basically is spitting those chunks of hail out the top of the cloud. So, and launching it. But yeah, any questions on this thunderstorm? So that video talked about squall lines, right? So squall lines are extremely dangerous. They're when we see, oh, there you go. That's a good shot there. But the squall lines will, so it's the most effective barrier to air traffic because the line is usually too tall to fly over, too dangerous to fly through or under, and difficult to circumnavigate. About 25% of all U.S. tornadoes are spawned in the squall lines. Okay, so extremely dangerous storm systems. But typically we see these squalls form over the plains and the Midwest, from the Midwest to the what do you call the states along the Mississippi? I'm totally blanking right now.
Bible Belt.
Yeah. So yeah, basically, right? So mostly in the central United States is where we're going to see these squall lines form. Like I said before, the air mass thunderstorms are typically what we're going to see over mountainous states, so more the western states. But in the central United States, we tend to see these squall lines form. And they're much, well, I mean, you guys have seen the news. You guys have seen what these storms are capable of producing, but typically these storms will hang out for long periods of time. These air mass thunderstorms that we have over the mountainous areas, they'll pop up and dissipate pretty quickly. Denver is a prime example of these air mass thunderstorms that just kind of pop up during the summer, especially over the Denver area. You'll have just random storms pop out throughout the day and really mess up air traffic. Like it says, the thunderstorms are really the most effective barriers to air traffic. The number one hazard for aircraft. I kind of mentioned today how bad it's, well, this weekend, how bad it is, how bad it's been for dispatching. What happens is, and it's died down quite a bit from earlier today, but we'll have these areas where we'll have these severe thunderstorms pop up, and they'll connect over an area. Well, with how severe the storm system is, sometimes we can't fly through that area. Remember, a lot of these storm cells have the potential of reaching 40 to 50 to 60,000 feet high, especially in the central United States. So let's say that we're flying from Cincinnati here, and we're trying to get to Detroit. It's going to cause either delays or a huge amount of a need for a reroute, basically, where we're going to have to come out here and then come up behind the storm system. So a lot of fuel used just to get out and around this storm system. Today, for example, we had, let me zoom in here. In Chicago, we had a very big storm system pop up, and it just kind of hung out right here. I had a flight coming in from Minneapolis to Chicago. I had him loaded up to the gills with fuel. He was in an ERJ, and I think he had like 13,000 pounds or something like that when he took off. So Minneapolis right here, Chicago right here, right? Typically, that burn in an ERJ is going to be somewhere around 5,000 pounds. He had like a total of 13,000 pounds. So he got about right here, and he notified me. So the route coming into Chicago kind of comes up like this, kind of like that. He notified me about right here that he was going to be holding at this point. You got Madison right here. You got Milwaukee right here. So, and I planned his alternate to be Indianapolis because it was a really far alternate. That's always good. Like Indy is almost always good weather. So I planned a really far alternate to allow for me to either add more hold time and give him a closer alternate, basically to give myself some options if we started, running against a wall, if he burned, if he was getting low on fuel, basically. So he told me he's going to be holding here and he was going to have 8,000 pounds of fuel on board still. So I said, well, don't go to Indianapolis. We'll change the alternate to Madison here. And I want you to hold as long as you can there. Chicago, the storm system was heavy rain and thunderstorms, and it was parked right over Chicago. So he started holding right here, and he was holding for about 12 minutes, and they said, okay, they cleared him in. When he got to about right here, they put him in a hold again because he was a high men's captain, so the landing minimums dropped below high men's, went down to half a mile. And remember, with a high men's captain, the minimum that we could ever get with a high men's captain is 300-foot ceilings in 1 mile. So it dropped down to half mile in Chicago for visibility, and so they put him back into a hold. I could see the storm system was about to move past it, and I knew the burn to there was 410 pounds. And I was just like, oh man, hold on, please. Give me 15 minutes and I know you're going to get cleared into Chicago. The storm system will be passed by then. And he was scared out of his mind. He was like, if I go to Chicago, can't get in, and then have to go to Madison, I'll land with 3,000 pounds. I'm like, great. That's an hour and 40 minutes of fuel. That's plenty. And he didn't like that response. But he's like, well, I'm a high men's captain. He's like, I'm just going to bug out. So I said, go ahead. So we sent him over here to Madison. What happens when there's a storm system over the field here? So Chicago, when he was in the air, went into what they call a ground stop, where absolutely no traffic's allowed into Chicago at that point. Which is kind of a problem, right? When you're up in the air, the last thing you want to do is run out of fuel and have that problem on your hands. But anyways, it's what happened was they were in a ground stop when he landed in Madison. I had built up his new release, and because I had to do a new release, his to get from Madison to Chicago, he had to, like, he couldn't take off for Chicago, and as soon as they lifted the ground stop in Chicago, they put him into a ground delay program. So the storm system had moved past. Had he held for another 10 minutes, he would have been cleared into Chicago, because I could see all these other airplanes all around Chicago holding. And by the time he was wheels down in Madison, all these aircraft had been cleared into Chicago. And they had 4 miles of visibility at that point. So anyways, what happened was when he landed in Madison, he got in the ground stop. They lifted the ground stop after about 15 minutes and went right into a ground delay program. He had to wait an additional hour and 30 minutes with his passengers on board until he could take off again for Chicago. So, kind of a big deal, right? These storms can really change your day. But yeah, when they divert like that, they can't let the passengers off the airplane. They can offer egress, but what happens is if somebody leaves the airplane, then they're on their own. The airline doesn't have to offer them anything, doesn't have to try to accommodate them, doesn't have to give them vouchers for another flight or anything like that. Once they're off the plane, they're done. So, kind of a pretty huge deal as far as like weather impacting a field. Just a good example of what happens. Something that we use on a daily basis, as well as a chart we call the TCF. So this is a thunderstorm forecast. So thunderstorm convective forecast, and it highlights areas where they believe there's going to be severe thunderstorms. So we'll use these. Go back to our map here real quick. Try to get both of them up at the same time. So anyways, you can compare what we're seeing on this chart to what we're seeing on our radar here. You can see that this storm is building here, and you can see that it's forecast. Something that this chart does will also tell you where they expect the tops of the clouds to be, and the solid dashed lines here mean that it's supposed to be severe, like high chance of severe thunderstorms. When we see these little dashed lines, it's like a medium chance of a severe thunderstorm. But this is pretty much an imminent strong thunderstorm, and we can see that develop here on these charts. You can see right here, these storm cells are, the tops are at 50,000 feet. Kind of crazy. So those TCFs used in conjunction with our radar, we can see these storm systems build. So kind of looking at the radar summary and then thinking about what we've been talking about today, can you guys identify what kind of pressure system we probably have right here? And what kind of pressure system we'd have right there?
Wouldn't they both be high pressure systems?
So my guess is that we probably have a high pressure system right here, and then it's probably being pushed by a low pressure system either right here or right here. And this would probably be a high if the low's right here. And you might have a low right here as well. So let's take a look at this real quick and see if we were right. Pretty good. So yeah, so low, low. The high is kind of right in between them. I was expecting the high to be a little more out here, but then another high pressure here with a trough or a elongated low pressure system coming up the center. So what direction is a high pressure moving again?
Clockwise.
Clockwise and down.
Clockwise and down. Good. And a low pressure?
Counterclockwise and up.
Good. All right. So what are these called again? Does anybody remember that?
Fronts? No? Maybe?
So these are our fronts right here, the blue and the red. Those are our frontal system. But these right here,
The trough.
these 10 long lines here. So the trough would be this one right here. You can see it's kind of like an olive green. And this is something I think we went over last week. It's kind of a harder one to remember. Let's see if we can zoom in here a little bit. Okay, there we go. So these light tan lines are what we call isobars. Does anybody remember what they do? What they're identifying?
Also, something to do with winds, like stronger winds. If they're
Kinda.
like wind.
It's kind of like wind, right?
Atmospheric pressure.
Yeah. So this is our pressure gradient, right? So what this is identifying is where our pressure, basically how rapidly our pressure is changing. So remember, a low pressure is these lower pressures. The gradients are going to typically be a lot closer together than a higher pressure. Higher pressure, it's a much more smooth transition from isobar to isobar. And we see a very little pressure change across the isobars. Okay? Whereas a low pressure, I don't know how to zoom out. Oh, zoom out. Okay. So let's zoom in over here. Okay. You can see that around a low pressure, we have a much more rapid change in our pressure. So this is 102.8. I know that's hard to see, but 102.8, you've got a 1012, 1016, 101, 1020. So these numbers here are millibars or hectopascals, right? So this is when we're talking about barometers. This is the metric system of measuring our pressure. In the United States, we use the inches of mercury, okay, to identify our pressure, to read pressures. But these charts are all using the hectopascals or millibars. So yeah. So let's keep kind of reviewing some of the stuff we've talked about today. What is this called again? This olive colored line here?
That was the trough.
Okay. And what is this pink one next to it?
Obscure front.
Occluded. Yep. Good. And if we have a long line of these red ones right here, what would that be called?
A warm front.
Dry line.
Warm front. So the dry line, remember, is going to be
Oh, yeah.
line, and then it's got like the ribbon lace or whatever you want to call it going down the side. Okay. What is this one called here?
Cold front.
Cold front. Good.
Can you repeat what the pink one was?
Oh, yeah, this one's an occluded front. So OCC LUDED or something like that. Occluded. I'm horrible with spelling anymore. I don't know how.
And the olive color, what was that name?
That's a trough. So
How do you spell that?
TROUGH.
Okay, that's what
I think. So remember that these troughs are elongated areas of low pressure. Okay. Oh, what is this called right here? What is that frontal system? You can see it all along here. Stationary front. Okay. So what is a stationary front doing? What's its movement?
Not much.
Yeah, stationary, right? Good. And what do we expect?
I'm sorry, Garrett. A trough is an elongated line of
Low pressure.
low pressure.
Yep. So what kind of weather can we see associated with a stationary front?
Stable.
So we're
No.
gonna stable unstableness. So we're gonna see storm systems develop along these stationary fronts, and they're just gonna linger. They're just gonna hang out a lot of times for long periods of times.
Okay.
What kind of what kind of weather do we associate with cold fronts? So we want to take a stab?
Like thunderstorms and rain and hail and stuff like that.
Yeah, so typically the cold fronts are going to be a little more violent of a thunderstorm, right? And we're typically going to see those storm systems form along the frontal line. Okay. And what kind of storm? Yeah, rapid moving. Good. What about a warm front? What kind of movement do we see with those?
Slower moving, quicker to dissipate.
Yeah, so it's going to be a slow moving, stable air mass, right? So we'll still see storms pop up along the edge of a warm front, but they'll be a lot more stable. Probably just like, a little bit of rain, maybe, but typically all of the air behind the warm front is going to be clear, right?
Is it like the difference between a spring shower and a summer thunderstorm?
Yeah.
Okay.
So we'd be more likely to see a squall line with a cold front.
Yeah, so typically we're going to see a squall line pop up near these stationary fronts because we get that shear, remember? So we've got air moving that way and that way. And what happens is since they're rotating in opposite directions, they start rotating, and that's where we see the squall lines form. So we'll see this break off into an occluded front and could see some potential tornado systems happen off the tip there. If not tornadoes, just rotation in the clouds and heavy thunderstorms typically. This one's starting to dissipate. Earlier today it was an occluded front, so coming off just like that one right there. So, yeah, good. You guys, feels like you guys understand that pretty good. Let's see here. So, just trying to think of, okay, microbursts. Okay. So we've got another video on microbursts in our outline here. Let me pull it up. This one's only 3 minutes long. But let's take a gander at that, and then we'll talk about microbursts here.
Could we have like 5 minutes afterwards of a break?
Sure, that works for me. So let's just plan on meeting back on here at 8:15. So what did you guys think of the downdraft or microbursts?
Pretty crazy. Actually, there was a video right after that showed of actually people recording them. It's like, it's weird because you see the weather's kind of calm and windy, and all of a sudden out of nowhere, it's like trees just fall straight over.
Yeah. Yeah, exactly.
And how fast it just shows up.
Yeah. So, extremely hazardous to aircraft, these downbursts, right? What was I can't remember, did it say an average altitude at which these are occurring? I know it's not high, but so from the base of the cloud. So on the surface, right, it's only affecting about a 2 to 2.5 miles. So what happens is these downdrafts or microbursts typically happen in aviation. We see them at the ends of the runway on the approach. Okay. So what happens is we have this extremely strong wind. So we just had a thunderstorm roll past, right? So evaporation and precipitation drag forms downdraft. Once it impacts, it quickly accelerates and strikes the ground and then dissipates. Okay. So these downdrafts or microbursts, I think their average life cycle is something like 2 to 5 minutes, and then they're gone. But extremely dangerous because of the high-speed winds. So what happens is, as the pilot's flying on approach, remember that when we're flying, when we're landing, we're always going to land with a headwind, right? Because it helps the aircraft generate more lift and helps slow us down. So we always want to land with a headwind. So this guy's coming along on his approach into the runway. So what happens is he encounters this microburst. So like it showed is as it comes down out of the cloud, it's coming down and basically flaring out in a conical shape, right? Just forms this cone of wind. And we'll see this wind reach speeds 20 to 50 miles an hour even, right? So what happens is all of a sudden the airplane goes really high off the glide slope. We see the airplane climb. And so what the pilot does to counter that is our thrust actually controls the height or our up and down on our approach. We don't manipulate the flight controls so much, but our thrust is actually what's going to raise us above or below the glide slope. So what the pilot does is he'll cut power. And as he approaches the core here, those winds are the strongest near the core. And so he's cut his throttle almost all the way out at this point, and he's pitching the nose down, trying to get back on the glide slope here. Well, as he hits the core, the wind's coming straight down and pushes the aircraft down very rapidly. Okay, at this point, the throttle's pulled out all the way, and he's barely producing any thrust. Remember what I said about these bigger jet turbine engines. What happens is they can slam the throttles all the way forward, but it takes a couple of seconds. And when I say a couple of seconds, it can be several seconds, like 10 to 15 seconds before the aircraft starts producing max thrust again. So he gets pushed down rapidly as he comes out of the microburst, out of the center of the microburst, and encounters a tailwind. So the tailwind's extremely bad for airplanes on approach. What happens is a tailwind will actually push the aircraft down into the ground faster. It requires more thrust to overcome the tailwind than it does in a headwind. Okay, so it's actually taking lift away from your wings. So he'll jam the throttles all the way forward, which will speed him up quite a bit, but it takes a while to do that. And so what he's going to try to do is, because he's descending so rapidly, he's going to try to pitch up, and a lot of times he'll go into a stall and crash just short of the runway. So to counter this, they started putting in these little probes on the approach, and we're gonna get into this microburst crash here that Dave posted. But because of this crash here, the Delta 191, they required that they build this low-level wind shear or microburst detection system. But what happens is there's several probes that are placed along the approach path into the airport. And what happens is these probes will detect wind shifts and put out a warning of microbursts occurring at the airfield. But yeah, so what I want to do now is kind of go over that accident. So let's see. I wish they still flew these airplanes because they just look awesome. It's called an L-1011. But I want you guys to watch this video. Let's see. I know there's... Yeah, so this is one of those aircraft investigation videos. Posted in.
Is that the one that Jeff just posted into the chat?
Hopefully it's the same one I was thinking of. What is going on with my internet? Yeah, this is it. So everybody, click and watch Jeff's video really quick, and we'll jump back on.
Okay.
Well, that was terrifying.
Yeah. So,
Yeah, that was.
No, thank you.
yeah. So,
To be fair, though, all of aviation is polished and rated
yeah, exactly. But, this forced the FAA's hand into developing that low-level wind shear or microburst detection system. you know, it really accelerated the development of the system. So yes, it's sad and it's horrible. It really is. But like you said, if there's one thing that we could look back and say helped make aviation more safe, it would be this crash, you know. But yeah, microbursts. Like I said, they're typically going to be following behind a thunderstorm. You know, the dissipating stage of the thunderstorm is when we're going to see those microbursts happening, and that's due to those strong downdrafts, like I was talking about previously. In that dissipation stage, it's just a rapid. The clouds just disappearing, right? So it's just strong downdrafts that are going to create these microbursts. It's going to create that strong hailstorm, heavy rains, and so on. So pretty scary stuff as far as, you know, the microburst goes. But because of that crash, it is much, much, much more safe because of the system they developed. I don't think there's been a microburst airline crash since this one. Microburst related crash since this one. So so the shelf clouds, right? So this is also part of the thunderstorm. One of the main problems here is the icing. Okay, whenever we have these huge, massive, just storm cells like this, with the shelf clouds way up high, typically it's going to create those supercooled liquid droplets and cause severe icing problems. A lot of that's due to the convection of those clouds. You can see how far out this cloud has developed. Oh my gosh. You can see that it's several miles from the center of the storm system over here, several miles outside of that. So what's happening is this storm system it's building that convective activity, and we're still seeing this strong convection. But as the water gets high altitude, it cools, even freezes. But because of the surface tension of those water droplets, sometimes they don't freeze. They stay in their liquid state until something breaks the surface tension of the water droplet, like an airplane. At that point, it instantly turns to ice. And we talked about the effects of icing on aircraft last week, but extremely hazardous weather. And we talked about the FAR that states no dispatcher may dispatch an aircraft into any known severe icing. So if there is severe icing occurring, we can't fly in there at all. It's extremely dangerous.
So sending an aircraft into close encounters of the third kind like this is not a good idea.
Yeah, so
I'm just making sure.
Yeah, so just be, you know, a lot of times they'll do what we call an air met, and I'll show you what these air mets look like. But these air mets identify areas where there's likely to be icing occurring. It'll even tell us what type of icing. moderate icing, and it'll tell us the flight levels that the icing is likely to occur. Until we actually get a pilot report that states that severe icing is occurring, we can still fly through these areas. Just because it's forecast doesn't mean it's necessarily going to happen or is happening. So we can still fly through them, but once we see a severe icing segment, at that point we have to go around that area. So, typically when you encounter severe icing, your immediate reaction as a pilot is to get out of it. If that means ascending above the precipitation or the visible moisture, going below or going laterally, depending on what type of cloud the icing's occurring in, is going to dictate what direction you go, right? But you're going to get out of it as quickly as you can. But as soon as that PIREP appears saying that there's severe icing encountered in an area, nobody can go in there at all. You have to route around it. So that's one thing that we watch for frequently. Even if it's forecast, typically we need to get a report. Let's say that it's forecast severe icing over, let's say, Cedar City right now. If it's forecast severe icing over Cedar City and that's our destination, typically what I'm going to do is I'm going to call the station and I'm going to say, has there been any reports of severe icing on any of the aircraft that have departed or arrived in there? And I want to see if anybody's even brought up the icing conditions. If they haven't, I'll dispatch in there all day. But if there's one plane that has reported severe icing, I have to delay or cancel or delay out the flight, or if he's already in the air, then I'd probably tell him to divert. So.
What guidelines or parameters are you using at that point, Garrett? So if the PIREP or if the report was, say, 8 hours ago.
Mm-hmm. So PIREPs only last 30 minutes. So PIREP is only valid for 30 minutes. If a PIREP has been reported in the last 30 minutes, then it's a no-go. If it's been reported 30 minutes ago, or let's say 45 minutes ago, and they haven't had another aircraft flight in that area, I might hold off for a little bit. But it's really at the discretion of the pilot in command and the dispatcher. At what point do they feel like it's safe to even test the waters? Let's say it's been an hour since a severe icing PIREP has shown up. What I'm going to do at that point is I'm just going to say I'll notify the pilot in command and I'll tell him, hey, there was a severe icing PIREP over this area an hour ago. It's no longer there, no longer reporting. Use caution and enter at your discretion, right? Leave the choice on the pilot in command because he's the one that has to deal with the responsibilities of flying through that area. But if it's no longer occurring at that point, technically I'm legal to dispatch through the area.
Okay.
Good question. So we haven't really talked much about diversions. But trying to think. So diversions are going to happen every single day in the OCC, right? We're going to always have weather somewhere that causes somebody to divert, or an in-flight emergency that causes somebody to divert. Somebody in the OCC is always going to get it, right? In the case of a diversion, there's a lot of factors that we got to take into consideration. We talked about, what qualifies an alternate as a good alternate when we were going through the FARs, but making sure that they have fuel or maintenance or the ability to handle the passengers, things like that, all super important when we have a diversion. So when we're looking at, just yesterday I had actually, while Michelle and Ash were there, I had a flight that was going from St. Louis to Chicago, and he had there was a storm system over here, and then there was a storm system over Chicago, and he had what we call a wing sensor overheat for his anti-icing. And so basically what his handbook told him to do was he could not fly into icing conditions anymore. He was actually into this storm system already, and he said that he was building ice on the aircraft. So he hurried and descended and got to about 15,000 feet, and Chicago was a no-go, just with an overcast cloud layer and the temperatures were below 10 degrees C. Chicago was out of the question. So, one thing that we need to do is we need to immediately contact our regional controller and say, hey, I have a diversion. This is where I'm going. So what we do is we choose where, did we choose an alternate for Chicago? Maybe, maybe not. So we need to look at a couple different things is, where, at what point am I going to be diverting and at what altitude? So where's somewhere close enough that I can reach with the amount of fuel that I have on board? So he ended up going to Indianapolis.
Hi.
And we have a maintenance base in Fort Wayne. I had asked the system controller, where do you want him to go? I said, Indianapolis looks good. Fort Wayne looks good. And he said, just send him to Indy because Indy was already listed as the alternate. So I sent him to Indy. And he was about right here, and we lost the ACARs.
Dad, are you
So
going
I
to
couldn't,
call for watermelon?
So I had sent him a message and said, hey, we're going to have to send maintenance down from Fort Wayne. So if you can make it to Fort Wayne, that's even better. But he didn't get the message. So he went all the way into and landed at Indianapolis before he ended up getting the message. But what happens at that point is, if it's not a station that we have maintenance or somebody to solve it, we have to send maintenance from a station to come and fix the airplane before we can depart again. And oh my gosh. And sometimes that causes flights to delay for long periods of time. Like this guy, because we had to send maintenance, the delay was hours. Okay. So a couple things to think about as well is captain, like crew duty time. So our crews each have a certain amount of time that they can be scheduled to, even like from when they show up at the airport to when they, can leave, basically. So that's called their duty time. Okay. Then they have another time that's called block time. So duty time, is, I can't remember what it is, and who's my crew supporter?
I haven't done crew support for a while, but I did it a while ago.
Yeah, so do you remember the duty time? It's something like 14 hours, right?
It depends on when they start. It's anywhere from like 12 to 14 hours, I think.
Yeah.
For FTP?
For their duty time, yeah.
Yeah,
It
it's gonna
depends
be
on
for
whether
9
or
and
not they were on reduced rest the night before.
just flight attendants or for pilots?
Pilots.
Pilots, yeah, no, it doesn't have anything to do with their rest the night before. That's just flight attendants. For FTP, it's on table B, so it could be anywhere between 9 and 14 hours. But they can be extended an extra 2 hours depending on their day and if they've been extended the day prior.
There we go. Like I said, we've got our crew support here, so we're in good hands. But as far as block time goes, though, they also only have a certain amount of time that they can actually be flying the aircraft. So they've got a duty time where they can be at the airport, and it's just their entire day, and then they have a block time where they can actually be flying the aircraft, and a limit to both of those. And so what happens is, in the case of a diversion with a long hold due to maintenance or whatever, they have to stay on the ground for a long time. A lot of times we have to have our customer service coordinator come in and offer accommodations to take care of our passengers, whether that be hotels. They got to send a bus to bus them over to the airport they should be at, or to the area they should be, things of that nature. It's, for long diversions that they don't expect to be fixed in a quick amount of time, or it's an outstation to where they don't have a backup crew that they can swap in there. These diversions can cost a lot of time and a lot of money. But then there's also those times where, like my diversion today to Madison, diverted from Madison to O'Hare. Basically, he touched down, put fuel on the airplane, they patted him on the back and sent him back out. Now, he had to wait an hour and a half, but we call those fuel and goes. So diversions can happen at any time, anywhere, but they're all handled very differently. Just depends on the circumstances of what's going on. If they just need fuel, let's get them back up in the air as quickly as possible. A lot of times we'll even have the release ready before they even touch down. We'll build up a release, and the second they touch down, we'll send the release, tell them how much fuel they're going to have on board. Get a game plan together with the captain, and then get them out of there. But maintenance delays, and when we're talking about outstations like Minot, where it's just you're out in BFE, it's going to be treated much differently if you have maintenance issues on these different outstations. So. Does anybody have any questions about that, or?
No, we're good. My head's just ready to explode. We're fine.
We're fine.
So, question regarding your diversion when you were, this map that you're showing right now, it shows icing conditions, and you had diverted him over to an area that would be on that. It was talking about with his icing equipment or de-icing equipment. You couldn't, if that had been an area of icing, you couldn't divert to that area, could you?
Kind of going over my previous statement. It depends. You got to remember that these are forecast, so not actually occurring. Just kind of saying, hey, it's possible that icing's going to be here. You know, we just got to remember when we start talking icing problems and no icing aircraft, we've got to take some things into consideration. Where am I going to be hitting my freezing level? So at what point am I going to be below 10 degrees C, and what are the cloud conditions, right? Broken clouds, he can still dodge the clouds if he needs to get into a station. If it's overcast, it's probably not a good idea to send him in there because that means complete obscuration, right? So either he's going to have to fly under the cloud for a long period of time, or at one point he's going to enter icing conditions. So, you just got to take into consideration, where's my clouds? At what altitude am I considered to be, in icing conditions? And you just kind of got to take that all into account and make a decision off of that. In the case of this one, there wasn't an icing air mat when I had sent it there, but like today, if it were today, right now, and he was being sent to Indianapolis down here, and it's in this air mat, I would just have to make sure I'd go into the text here. You can pull up what's going on in Indianapolis right now. Okay, so this is the current weather. Right here, this is the current weather in Indianapolis. Okay, here's my temperature, and then here's my cloud conditions, my sky conditions is what we call them. Okay, so I've got few clouds at 7,000 feet, scattered at 13, and broken at 25,000 feet. Okay, so technically he could probably still get through the cloud layer. In this case, the pilot had gotten almost to 25,000 feet when he had the message pop up. And so he would have been just fine. But basically he's going to have to maneuver around the cloud systems to get below to a level where he can fly. I'd also look here in the TAF and look at what's going to be happening in the near future. Okay, right now it's like 3Z. This isn't supposed to be happening until 9Z. Okay, 9Z. That feels right. 3 or 4 o'clock Zulu. Anyways, so this isn't supposed to be happening until 9 o'clock Zulu. This 15 broken at 1500 cumulonimbus. So that storm's not supposed to hit till 9Z. So if I were diverting there, I'd feel comfortable sending him here with this weather because there's a good chance that he's going to be able to see and avoid the clouds, right? Remember, the icing conditions are 10 degrees and below with visible moisture. So as long as he's staying out of the visible moisture, we're good to go. And I definitely, when it comes to diversion, I definitely inform the captain. I don't tell them you're going to Indianapolis. I inform them that Indianapolis looks good to me, and then I send him all the weather information and say, what do you think? You always want to leave it in the pilot's hand because they're in the cockpit and they can see what's going on around them, and they can make a better decision on how they feel. So, and really, they're the final authority either way. So, does that answer your question?
Yes, sir.
Okay. But yeah, I mean, like I said before, we're just going to take into consideration all of the factors leading up to why are we diverting, and what is the safest and best alternative, or safest and best route or action plan, you know? So, anyways. Let's see here. So, we've finished this off. Just want to double check, make sure there wasn't anything important that I missed. We looked at hail, tornadoes. Here's your, you guys have.
I legit thought you just said, what the hell?
I did. No. So that's like one of the bigger pieces of hail that you'll ever see. But anyways, this is the F scale, or the Fujita scale for tornadoes. So if you've ever heard of an F1, F2, F3, F4, F5 tornado, this is how they rate the tornadoes. So they look at a 3-second wind gust, and that determines the scale, right, of the tornado. Remember, tornadoes is when the cloud actually touches the ground, or the rotation actually touches the ground. If it's still in the clouds, we just call that a funnel cloud. It hasn't actually touched the ground. There's also one more, and that's when it's over water. When it's over water, we call that a water spout. But this is just the rating system for that tornado. So not super important, just kind of a cool thing to look at. But yeah, something else that's kind of interesting is like these F5 tornadoes have a surface area of like, it's upwards of like 5 miles wide. It's extremely huge, all-out destruction. But that pretty much covers the material for today. And we're kind of too late to start anything else. Tomorrow, Adam's going to be teaching, and he's going to be talking about the weather reports. So he's going to help you guys start decoding weather. This is also tomorrow will be one of the last days of weather. And then we go into practical dispatch application. Well, I think we do like CRM and DRM. But then we're going to start going just full tilt into prepping for our flight planning. And we're going to do a lot of practical dispatch applications. So I'm going to have you guys reading NOTAMs and PIREPs and METARs and TAFs. Are we legal? Are we not? Do we need an alternate? And we're just going to hit that as hard as we can. It's going to feel very redundant and everything when we're going through the last part of this week and the rest of next week. A lot of the material is going to feel very redundant, but it's super important and probably the most difficult thing to fully comprehend when you're dispatching is legalities and and alternate requirements. So so we'll go headlong into that and really hit that hard. But
So what are we looking at as far as weather quiz?
so depending on where you guys get tomorrow with Adam, the quiz will probably be either on Thursday or Friday.
Okay.
So we'll just kind of evaluate it on Wednesday, see where we're at. But we should be closing up weather no later than Friday at the very, with the quiz, finishing it off with the quiz no later than Friday at the beginning of class. So
Garrett,
The last
I sent you.
yes, and then I was going to talk to you, Eric, as well after class, if you don't mind for a second.
Okay.
Have you graded the last exam?
That one I have not yet. I was going to get to that tomorrow, but
No, really, feel free to take your time.
sorry, but yeah, those will be online tomorrow. But other than that, the turbulence video is now in the Google Drive for today. Just pull that video up and watch that to end the class here. But any other questions or?
Thank you. Very helpful tonight.
Yeah.
Nope, I think I'm good, thanks.
Alrighty. Well,
Yesterday was very enlightening, I think.
yeah.
And, yeah, very enlightening.
You enjoy it?